안녕하세요. Thank you all for staying for the last session. It won't disappoint. I will have many demos that we're going to try out together with you as an audience. So let's have some fun. Now, before I get started though, I want to make a point about machine learning really being available in our entire life, pretty much everywhere. Doesn't matter if it's a self-driving car, a voice assistant, if you use email, there's spam email filtering. If you go to an airport in places in China, you have facial recognition check-in, or if you use a credit card, there's a fraud detection algorithm behind it. Machine learning pretty much sits everywhere already. And today, we want to look into elements of computer vision and natural language processing, and I brought some devices with me to try this out. But there's a change in the way we build applications. Traditionally, we had to learn how to type a command line or how to operate with a computer. Nowadays, applications adapt to us. We use computer vision, natural language understanding to talk to a computer to have a natural way of interacting. And this really goes into three categories that I want to talk about today and showcase in a demo: natural language understanding, automatic speech recognition, and computer vision. And deep neural networks have helped us to get a lot better at this than we traditionally used to be able to do. One example, you heard about this earlier, you could try it out in our expo hall, would be something like the Alexa voice services. Having a device, like an Echo device, that runs a machine learning model on the device itself, so we can start talking to it, and a machine learning model in a cloud computing environment, so that it can give us intelligent responses. And if we think about these assisted interactions, they can be intelligent voice responses in a call center. We had a demo of that earlier. That can be chatbots, Facebook and Kakao, doesn't matter. Whatever you want to have automated interactions. The idea is you split it up between two types. One type, automatic fulfillment, because I understand what the customer or the user requests, I automatically fulfill. Or maybe I funnel it into the right direction, to the right agent, to the right person that can help me here. Now, another element of new interactions that we see is all about computer vision, primarily facial recognition. There are places in the world where you go into a hotel and you will be recognized as a loyal customer so that you can get a faster check-in using facial recognition. We see it in a variety of countries that immigration departments use a camera together with your passport to let you pass through. All of these are examples on how we create more natural systems to interact with. But one thing that we haven't talked about today yet is augmented and virtual reality and how that ties back to machine learning and natural language interfaces. So what I wanted to do today is showcase to you a product called Amazon Sumerian, which is a browser-based, web-based interface that allows you to create virtual and augmented reality experiences and then deliver it to the tablets, to the desktops, to the phones, etc. And we're going to try to integrate that with Amazon Lex, so that we can have a virtual reality, a host. We call these people a host, and are able to talk to them, and they give us information. So the demo that we try to do here is, imagine you would enter a bank somewhere, and there's a screen of a virtual receptionist that I can start talking to. So let me switch over to my laptop here. There we go. And what you see here is a browser-based interface of Amazon Sumerian, and it allows us to play around with these entities here. I can zoom around. Let me change the camera around here a little bit. I'm based in Hong Kong, so I created this little interface with a few towers of Hong Kong. You can see that it allows me to modify these objects any way I want, all done in the browser. And if I click on this lady here, you can see on the right side that I can integrate it with Amazon Lex through the interface of dialogue and give her a voice using Amazon Polly by integrating it with speech. Now let's try this out. If I hit the play button, see what's happening here. This will be loading up the scene. There we go.
Welcome to Ollie's fictional bank branch. My name is Candy and I'm here to assist you today. I am an Amazon Sumerian host and I'm integrated with Amazon Lex to create a virtual assistant experience. What can I help you with?
And you can see that if I change the camera around, she keeps looking at me. And one of the ways to do that is, if you have a screen, you can have a camera that looks at facial recognition. So if I move around, she will keep looking at me. Now if I hit a button here, I can start talking to her. Let me try that. What can you do for me?
You can ask me anything about our operations here, such as, for example, where to deposit your check, or how to deposit money into your bank account, or maybe which credit card you should apply for. Just ask.
Okay. Hit that button again. I got a check that I want to cash in. Can you help me with it?
Sure. To cash checks, please proceed to counter number 5 or alternatively use our check drop box outside of the building.
Okay, great. Well, what if I have another request? Let me hit the button for her to listen to me. I have money that I want to deposit into my account.
Okay, great. To deposit money, please proceed to counter number 10. You are in queue and your queue number is 305.
Great. All right, and you saw that she actually has a queue number for me. So Amazon Lex is calling an AWS Lambda function, which puts me into the queue, brings that information back to Lex. Lex renders the voice and brings it back to Amazon Sumerian. So great ways to actually be able to create more natural interfaces that we can use with an actual person that starts looking at us, tracks us with a camera, so it feels like a natural experience that we can have. So I mentioned virtual reality. How about augmented reality? Well, actually, Amazon Sumerian can also do augmented reality experiences for you. And as of last week, it is my pleasure that last week in Sydney, we announced a new functionality of Amazon Sumerian, which allows you to run augmented reality applications in the browser of your devices. So no app that you need to install. You just go to a URL and you now have an augmented reality experience in your browser. So if you haven't seen that, check that out. That's really, really cool. Now, if we think about augmented reality experiences, then we use computer vision under the hood to make that work. And very often, these are deep learning machine models. So I want to try a few of those out live on stage now here. Before I can do that, though, let's just look into the concepts. Now, Mushan, he just talked about this a little bit earlier, how we can use that with Gluon and MXNet. But what we're going to use next is a convolutional neural network, CNN. And the idea here is that the neural network that you create basically resembles the same network structure that we would have in the animal or human visual cortex. The idea is, instead of looking at a picture in a whole and running an entire algorithm over it, we look at specific focal points of interest in the picture. Just like a human being, if I look straight ahead, I see pieces in more detail here, but not here. If I look over, I can focus on it. That's exactly what we're trying to reproduce here, and that's very useful in image recognition, facial detection, and of course, video analysis. So another thing that we often want to do is, what if I have a video or picture, I want to identify what is that picture about, but I also want to know where exactly that object is. And one technique to do that is called a single shot multi-box detector. So you take a picture and you zoom into a region and you predict that region and you zoom in further until you find an object of interest, and then you build a bounding box around it. We have a blog post that explains how to do that with Gluon, so check that out. Very, very interesting. Now, this technique is very accurate, but it's not very fast because we need to look at many, many different pieces of the image, and we need to zoom in, zoom in, zoom in, zoom in. So lots and lots and lots of times that we need to push the image through a neural network. So a better technique, when we say we want speed, we want it fast, could be by using a technique called YOLO. You only look once. And the idea here is the person behind this, Joseph Redmond, he wrote an open source neural network tool in C called DarkNet. And in DarkNet, he implemented YOLO. There's a research paper on YOLO, if you want to know the details. And it allows us to take a picture, look at it once, and detect the object. And I said we want to do live demos. So let's try to do a live demonstration of an object detection here with the audience. And so I'm going to do two demos. The first demo, I'm going to try it out with the default data set that Joseph has trained it on, which is a data set called COCO, C-O-C-O. And then I'm going to showcase you how I trained a custom model on Amazon EC2 instances, a P3 instance, to recognize very specific objects. So let's try this out. I'm going to flip on my camera, fade over here. I close my bot here first. So let me bring up my first demo. We load up the neural network. There we go. And now you can see that in real time, it is able to actually identify what's going on. Lots of person here. Spot off. We go down here. You can see there's a TV monitor. I see someone waving. And we can see there's lots and lots of things that we actually start identifying. The key point here is this is really, really fast. So if I try this out on myself, you can see that this model is pretty reactive. It also tells me I should wear a tie. So you can see that there's a threshold. And if I just move this a little bit so you can see it better, you can see that it identifies with a certain threshold. So there's a percentage that's coming up on the side. So the tie is actually a low percentage, while the person is really fast. And the key point here is I run at 40 frames per second, 30, 40 frames per second, and I can do any kind of movements, and I detect really, really fast what's going on. Now, I said I had a custom object that I trained this on. So let me first load up my model here. It's my second demo with a custom model that I created and trained upon a very special object. Now let me get my object. There we go. Got a unicorn, and if I hold this up, you see it detects in real time unicorn. Feel free to pass that around. I think we have a few more objects that we can get there. And I'm going to handle the camera. And we can see how it quickly identifies if we have enough light now here. If I zoom in, if we can just turn the light up a little bit, there we go. We should see that it identifies the unicorn. Can you take that hot dog and move it around a little bit? You can see there's a unicorn coming up here. And you can see in real time, it can now detect these specific objects that have been trained. Let's try the hot dog. There's a hot dog. There you go. Got you get the hot dog that has been specifically trained for it also. And you can see that threshold is specific to it. And I think somewhere we had also another person I'm not sure where that person is, but I think somewhere here, something's happening. Someone's a hot dog man. Someone's hiding there. So we trained this model on custom-specific objects, in this scenario, hot dogs and hot dog man, which is a specific costume that I tried this model on. Thank you very much. Appreciate it. So, my clicker. The idea here is, yeah, you can feel free to pass it in front. The idea here is, how can I train a model with my custom objects? And I figured it would be fun to have some of these. But if you want to build a model like this yourself, is it complicated? Is it difficult? Let me share with you how I built this. This is the way it looks like. I went into the office with my big unicorn, and all of my colleagues were looking at me like, why do you bring a big unicorn to the office? I said, well, I need to train machine learning models. And the way it works is, you take pictures or a video, you hold it up, you turn it around a little bit in different lights, in different settings, and then you take those pictures one by one, and you start annotating where's the object. So I went ahead, I took these pictures, I said, here's the unicorn, here's the unicorn. Here's the unicorn, here's the unicorn. To give you an idea, for this demo, I took about 100 pictures of the unicorn, 100 of the hot dog, 100 of the hot dog man. And the training on a P3 instance, 5 minutes. That was enough to get the accuracy that you've just seen, which is pretty accurate. So that's pretty impressive. In 5 minutes, I can build a computer vision model like this. The problem is, this annotation takes a lot of time. I had to, every single image, I had to go through it. So when you build models like this, think about how services like Amazon Mechanical Turk can help you. Mechanical Turk allows us to make an API call against Mechanical Turk and specify a job. That job is being picked up by actual human beings, and you can tell them, annotate the unicorn, annotate my object, annotate my document, and you get it back via an API call. So it's a great way to build that ground truth data that you require to train your machine learning models. Annotate your raw data so you can start training it. Now, a few other things. I do object detection with unicorns. Is that useful? It's fun, but not so useful. So how is object detection actually used? Well, one example is self-driving cars or assisted driving in cars. So we have customers like TuSimple that train computer vision model to do object recognition and identification. If you can read Chinese, you can also see this one here, for example, is being detected as a Volkswagen because it is a Volkswagen car. And this is taken from a car that has been driving to the city of Beijing in China for a self-driving car. And computer vision helps us to go down to the pixel level of identifying where's the space between the street and the car, where the objects that I identify, and go down to centimeter accurate positioning of that vehicle. The technique that I just showed you can be used to do something like this. Obviously, you want to do a lot more training, but it is an example of how object identification is very, very useful. Now, there are a few other things here. If you think about building a machine learning model, training a model makes sense to do it in the cloud environment. Why? I have elastic capacity, I can access the latest and greatest GPU, CPU hardware. I can have thousands of them, and I only pay for the seconds I use that infrastructure. So that training I just showed you, 5 minutes, that's all I pay for it. If I make a prediction, well, if I make a prediction of something that sits in my cloud environment, then it makes sense to do the prediction in the cloud environment. Think an e-commerce website where you give a recommendation. People who bought this also bought that. That sits in the cloud, so the prediction should be done in the cloud. How about that self-driving car? When the car makes a prediction, does it need to go to the cloud? What if I drive my car autonomously, I lose internet connectivity? What do? I stop? Or I basically just continue, run over a person and be like, I didn't have Wi-Fi? Probably not very good. So these models actually run at the edge, on the car, in the phone, on my laptop. And there are services like AWS Greengrass, and specifically AWS Greengrass ML, machine learning, that allows you to easily deploy machine learning models that you train in your cloud, push it out to the device, and make predictions on the device. And it comes with pre-built TensorFlow and Apache MXNet packages for devices like Intel Atom, NVIDIA Jetson TX2, and also Raspberry Pi. Now, if we think about predicting something at the edge, we can be really, really fast with that prediction. So one of the things that we could do is do people detection. I want to share with you an open source project called OpenPose. It has been created by a team of researchers at the Carnegie Mellon Perceptual Computing Lab. And this is a really cool project because it's using deep learning to identify a human and know how he moves around in the poses that he does. So I figured, let's try to run OpenPose right here on my laptop and detect body and hands, and then report that back using Greengrass into the AWS cloud environment. All right, let's try this out. Flip my screen. And then the first thing that I'm going to run here is the OpenPose demo. Now, see, if I start running this, I'm going to take something that's a little bit brighter. You can see that it identifies people individually, is able to track them, and the specific hand or body movements that we have. Let me try this out. There we go. A few takers here. There we go. You can see here someone's waving. You can see that the stickmans can now realize how we're waving. Let me just try that on myself here, because it's a little bit brighter up here. You can see that it actually identifies in real time my movements and can track those very specifically using computer vision. Now, one fun thing that I can do is I can create heat maps. And now I have a heat map of myself moving around, identifying all these specific. Let's just turn the spotlight off for a second. Thank you. And you'll see that with the light now, you can see that it's very easy for me to recognize my movements. Thank you. And if I push that back out here, we can see that it allows us to identify individuals and how they move around and how they sit using complete deep learning technologies here. So some really cool stuff that we can do. And you got to think about the fact that all of this runs at the edge location here so that we get a very fast response. But we report back information like how many people, what movement, back to my cloud environment. And if we build models like this, again, the training is done in a cloud environment, but then we push it out to the edge. And by the way, that's one of the reasons we also created AWS Deep Lens specifically here. AWS Deep Lens, the model runs on the device. So you train in the cloud using SageMaker, and then we run the model on the device itself. So think about when you build machine learning models, what belongs into a cloud, what belongs at the edge, and how do I use things like green grass to actually move things back and forth and send back the information from my prediction that I require to my cloud environment. Now, sometimes you want to use fully managed machine learning services. Earlier, you heard about Amazon Recognition, allows us to do object and scene detection, allows us to do facial analysis, allows us to do celebrity recognition, and so on. So I wanted to give you an example of how do we run facial analysis, both with recognition only, which would look like this. I have a camera, my webcam. I will take a picture for myself with JavaScript. I send it to Amazon Recognition, and I detect the face if I know the person. And then in my second demo, I'm going to try to do the same thing, but this time around, I'm going to use both Amazon Recognition, but I'm also going to use a local FaceNet deployment. FaceNet is a technique, there's a research paper on it, on how to detect your face. And I'm going to try to run that with TensorFlow on my machine, and when the accuracy drops, I use Amazon Recognition. Let's try that out. Flip my screen. Did I lose internet? There you go. Okay. Great. So let me do the following. I'm going to do an inspect element also, so you can follow down here at the bottom what's happening. And there are two interfaces to do this. Oops. The first one is to upload your photo with a name. That is to make one API call to recognition to know which person it is. I already did that beforehand. And then the second one is to go onto my webcam here, take pictures, and then identify the face, making one API call, so that I can start overlaying that face. If I hit this button, you see that it now starts to send API calls to Amazon Recognition. And if you look at the bottom, it will make these predictions pretty accurately, knows exactly that I'm here. And you can see that it's just an API call that it's doing. I get the JSON with the bounding box back, and I can overlay. And if you look there, this side, you can see that it's also recognizing myself as Olivier Klein. The benefit here is all I need to do, one API call. The problem that I have is it's fast, but not very fast, you see? Because it obviously needs to make an API call and needs to wait for the response. So one of the things that we can do is we can say, recognition is really good in giving me a very high, accurate facial recognition. So one other thing that I could do is, what if I run a local deployment for facial recognition? And in this scenario, I'm going to run a TensorFlow model that implements FaceNet. I'm going to try to tab onto my camera. And what it's now doing is it takes a pre-trained FaceNet model, loads it into my GPU memory here on my laptop. And the idea is that I can detect faces in real time a lot faster here, but the accuracy is not as good. But we will, when we detect the face, we can run it against Amazon Recognition. Let me just make this a little bit bigger. Activate the bounding boxes and labels. And if I now step in front here, let's see if it's a bit of the lightning. You can see that it's basically identifying myself. And this is really, really fast because I can move around in real time It keeps tracking it, and you also see that there are like dots on my face, and it recognizes Ollie with a certain accuracy. Now I'm gonna try. Sorry for the people sitting in front. They keep keep being used here. If we now zoom in and I try to focus, you can see that I can actually identify faces, but they're not trained, so they would all be unknown in that regard. And now I can use this as a baseline to say, well, if I know the face, great, right? Like this in this example, it detects Ollie, fine, I recognize it. And if I don't recognize it, or if the threshold is low, then I can take this, send it to Amazon Recognition, and get the information back. So you have that combination of local prediction and more accurate prediction in my cloud environment. All right. Great. So I want to leave you with a few points before I head over. When we do machine learning, there are kind of a few challenges. The first one is we need lots of data to train machine learning model, or we need to use fully managed services like Amazon Recognition. Now, there are great ways to use all the different AWS services to build data analytics, build transformation of data, store massive amounts of data, move data around, which is great to build your own machine learning models. If we train, we often need to have lots of GPUs, CPUs. We need to have them elastic. We need to get capacity to thousands of nodes quickly, but we only want to pay for the amount of time that we're using it. And if you're not familiar with the AWS Deep Learning AMI, have a look at it. It allows you with a click of a button to get a fully ready environment to train your models. And lastly, when we want to make predictions, think about when do I run the prediction at the edge? When do I run it in the cloud? It's generally a combination of both. Think about, do I use GPUs, CPUs? Do I do complete serverless predictions? And when do I run it at the edge? And if I do run it at the edge, how can I use Greengrass, for example? So here at AWS, we're here to help you with all of these challenges. So talk to us and see how we can help build your own interesting machine learning models in both computer vision, natural language understanding, and everything around recommendations and so forth. That's all I had for today. Please remember to fill out the feedback. We always want to hear what went well and what did not go so well. So please feel free to comment on that. And with that, I would say thank you. Kamsahamnida.